Hello everyone, today we'll be exploring the notion of continuity, which we'll explain using functional series, and we'll also delve somewhat into the notion of uniform convergence, which we will use later, which we'll leverage to prove what I just said before, that is the continuity using functional series, right? So let's come back for a quick moment to the notion of series. A series is defined as a sum, or basically a progression that abides by some laws, right? With the progression of some index number k of terms, which we'll denote as uk, right? Which grows by the rules of the series, right? For example, right, the series for e, right, to the x, this is a Maclaurin series, but this is still a series, right, is equal to, from k equals 0 of x to the k divided by k factorial. Right. This is a functional series, since this is dependent on the variable x, right? The convergence or divergence of this series is dependent on some variable x. And we need to write, of course, that this sum is still infinity. E itself is defined as a series, as an infinite series, from k equals 0 of 1 minus over k factorial, right? So this series is not functional, since it is not dependent on some variable x. As such, this series is just series. We'll denote it as a series. This is a functional series. Of course, if I believe in America, it is divided by groups calculus 3, 2, and 1. You study this in calculus 2. You study basically how to find the radius of convergence. You find basically how to find if a series converges or diverges. I believe in America, you call D'Alembert's principle the ratio test, right? It is basically the limit as k tends to infinity of ak plus 1 of ak, where the series is basically with terms ak, right? This is how you find convergence. This is actually called D'Alembert's principle. And you often also use the Cauchy-Maclaurin test, right? The integral test, as you refer to. But I digress. This is what you basically study in Calc 2, if I'm correct, of course. So there are two types of convergences. There's relative convergence, then there's absolute convergence. Absolute convergence is where the term as the index tends to infinity, right? Lim as k tends to infinity of uk is equal to 0. So basically this function at some point will abruptly end, right? Because the term will equal 0. It won't actually end. It will maybe go to negative numbers, right? Or it will grow once more. It depends on what type of series it is. But basically, this is absolute convergence, and there is relative convergence, which can be determined once more by relative convergence can be determined by D'Alembert's principle, Cauchy-Maclaurin method, Rabi's principle. I perhaps will sometime in the future make videos about them, but yes. And then in absolute relative convergences, there is also uniform convergence. So what is uniform convergence? Uniform convergence will define as follows. So suppose a functional series S of x, right? This is a functional series, which can be written as a partial sum till n of terms of this functional series with a remainder part, right? Rn of x. So if S of x is equal to some f of x, right? From 1 to, let's see, d, right? And n belongs to the interval from 1 to d, it's bounded by 1 and d. We can rewrite the series as f of 1 plus f of 2 plus plus f of n plus a remainder, right? Rn of x, where Rn of x is equal to f of n plus 1 plus f of n plus 2 and so on and so forth till f of d, right? It doesn't really matter if the series ends at some d or not, just let's suppose it does. Now in the radius of convergence, let's suppose there is some value x naught, right? For which there exists an epsilon bigger than 0 such that the absolute value of the remainder at the index of m of x naught is smaller than epsilon. Okay, so now what does all of this mean, right? It can seem very confusing at first. But basically what here we state is that at some value x naught, right? We can find a partial sum after which the remainder becomes infinitely small, right? And m is the index point, after which this remainder term becomes infinitely small. Not infinitely, but it becomes very small, right? So x naught is just some input which belongs in the radius of convergence of this functional series. But basically it means that for x naught, this series does indeed at some moment converge, right? And at Rm of x naught, the remainder becomes infinitely small. From this follows that since Rm of x for any x is bigger than Rm plus 1 of x, right? Rm plus 1 of x naught in absolute value is also smaller than epsilon, and so is all of the other terms, right? All of the other remainders. This basically proves that after some m, the remainder becomes infinitely small. If we change x naught to the value of the argument inside the remainder part, right? Since it's a function, right? We can plug in any argument. If this function if the variable remains within the radius of convergence, this equality will still hold true, right? Just m will change at some point. And then we can find or set some arbitrary number m, right? Which is smaller or equal to n, for which Rn of x is smaller than epsilon, such that x belongs to the radius of convergence. Well, this is a radius, right? So let's just to not cause confusion, let's denote it with capital R. All right? So for any value of x after some n which is equal or larger than m, which m is just an arbitrary number, Rn of x is smaller than epsilon. The absolute value of Rn of x is smaller than epsilon, with epsilon being very small. Now let's see an example which demonstrates this, since some of you might find it more easy to comprehend this concept using an example. So let's determine a geometric series, a functional series, defined as x plus x1 minus x plus x1 minus x squared, and so on and so forth. It doesn't end. Let's extend to infinity, or we can end it at some point d. It doesn't really matter. It won't complicate or tidy up the argument any further, right? It doesn't actually affect the concept itself, right? So let's note Rn of x as x to the power of 1 minus x to the nth plus x to the power of 1 minus x to the n plus 1, and so on and so forth. Here, by the way, this is not to confuse with the previous definition we gave for the remainder part, right? Since previously we said that Rn of x is equal to f of n plus 1, right? We started from n plus 1. But we might as well start it at n and just determine the partial sum of s of n of x to go from x to 1 minus x n minus 1, right? It doesn't really affect the notion of a partial sum or the remainder, right? It basically has no effect. So if you are confused with the fact why we start here, why we start the remainder here from f of n plus 1, and here we started from f of n, right? Since this is basically just f of n, it doesn't do any different, right? It's just the same thing. It doesn't really matter. It's just how you define the partial sum, right? If you define partial sum from going from 1 to n minus 1, then the remainder will go from n to whatever it is that the series ends with. If you define it as n minus 1, it goes from n minus 1 to whatever the series ends with. It doesn't do any different. So this term, the remainder, converges, or rather becomes, or can be defined as 1 minus x to the nth. And it is basically a function of x, since it depends on x. And from the inequality Rn of x is smaller than epsilon, the absolute value of Rn of x is smaller than epsilon, we can see that 1 minus x to the nth is smaller than epsilon. Here, seeing that 1 minus x and epsilon can be considered as bounded by 0 and 1, right? We'll consider that 0, epsilon 1, and 0, 1 minus x, 1, right? We get the following inequality. N times the absolute value of ln of 1 minus x is smaller than, or rather bigger, larger than ln of epsilon. Here, the sign of inequality changes due to the absolute value. This means that n is larger than the absolute value of ln of epsilon divided by ln of 1 minus x, which means that n is, as seen here, larger than some n, meaning that this sum is uniformly convergent, right? So the criteria for uniform convergence is met. Now, to determine uniform convergence, you can use the Weierstrass method, right? So Weierstrass said that a functional series, un of x, or uk of x, whatever you want, is uniformly convergent in the interval from a to b if all of its terms, starting from some index, let's say q, with any input value of x in this interval, will, in absolute value, be always inferior to the terms of the convergent series alpha n, which is basically composed of positive terms that are independent from x, right? This principle it's not really useful, since you will need to find some some series whose terms in positive terms whose positive terms that are not a function of x will be always larger than the corresponding absolute value of the terms of your functional series. And this is kind of hard to do, but essentially all sorts of tests that are done on series to see if they're convergent or not is boiled down to finding a series that is convergent, whose terms are always larger than the terms of the series you want to find is convergent or not. So this notion of uniform convergence will further leverage to prove that a function is continuous. And here is the theorem that we'll propose and prove, and which will lead us into the idea of convergence using functional series. So if all terms of a uniformly convergent series on some interval are continuous functions of x, then the sum of the series of these functions is also a continuous function. So let's define this mathematically in honor of David Hilbert. If we define some series of terms which are functions of x, such that u of n of x is continuous on a b on this interval, right? Then let's define this as s of x, right? S of x is also continuous on a b, right? Now let's prove this. So s of x we'll define as the partial sum of Sn of x plus Rn of x, right? Here we'll define the partial sum of being the partial sum of first n terms, and Rn of x is the remainder. Now let's choose some arbitrary value x, which will belong to the interval ab, and let's add some increment, right, to our function. So delta s is the small increment. You should know this is basic math, is equal to delta s of n plus delta of r of n, right? Meaning that delta s is equal to delta s of n plus Rn of x plus h plus, minus, sorry, R of n of x. This is Lagrange's theorem of finite increments. I believe that's how it's called in English. Either way, from here we can see that the absolute value of the increment or change in s is smaller than the absolute value of s sub n plus the absolute value of R of n of x plus h plus R of n of x. Here we just take the absolute value of minus R sub n of x, which turns positive, of course, since, that's the definition of absolute values. This series will assume that converges uniformly. Then, if it converges uniformly, we can choose some number epsilon larger than 0 but tending to 0, all right, such that for an index number m of 0 and being larger or equal to m sub 0, we'll have for n being equal or larger than epsilon sub 0, we'll have the absolute value of the remainder of n being smaller than epsilon over 3. So epsilon over 3 is just a very common notation to denote an even smaller number, which is of course well, not irrational, but it is decimal, right? 2. Since epsilon a priori is not divisible by 3. It will just lead to a very, very, very small decimal number. So for all values of x, this should hold true, which would in turn prove the continuity. So from the idea that for m sub 0 with n being equal or larger than m sub 0, this equality holds true, or inequality holds true, right? We'll have that the absolute value of error of m sub 0 of x will be smaller than epsilon over 3. This just follows from the details mentioned right above. And the absolute value of error of m sub 0, what is wrong with me today? R of m sub 0 of x plus h will be also smaller than epsilon over 3. Then, from here we can derive that s of m sub 0, the partial sum to m of s sub 0, will be a sum of a finite number of continuous functions, and will be a function that is continuous. And then we can derive further that this is due to the fact that we can take any arbitrary number delta bigger than 0, such that the absolute value of h, right, the absolute value of the increment, will be always smaller than beta, meaning that this function will in turn be continuous. From this we can see that not from this, from the inequality, you can see that the change in s of m sub 0, the absolute value, yeah, will be always smaller than epsilon over 3. Then, from inequalities shown above, this one, and the other one, right? The other one, I mean this one. We see that the absolute value of the change in s is smaller than epsilon, with the absolute value of h being smaller than beta, which proves that s is continuous on the interval AB if all the conditions above are met. Yeah, that's it.